Welcome back. We were discussing in electrical machine tutorial the single phase induction motors. We have discussed few problems related to double revolving field theory in tutorial 22, and now in this tutorial we will take the discussion forward and we will solve few problems related to the equivalent circuit of the induction motor single phase, and we will see how to calculate the circuit parameters like the impedance, current, torque, slip, and so on and so forth. Let us begin with the first problem. So the first problem is discuss the revolving field theory of single phase induction motor when you have the mechanical power output at a slip of 0.05 to be determined. The motor rating is given as 185 watt. It is a 4-pole machine. The input voltage is 110 volt. The machine is running at 60 Hz frequency, and the constants of the equivalent circuit parameters of the single phase induction motor is given, where 1 indicate the stator and 2 indicate the rotor circuit. The resistance and the reactance of the stator is given as 1.86 and 2.56 ohm, whereas the rotor circuit, if we see the resistance and the reactance under the standstill condition, is given as 3.56 and 2.56 ohm respectively. Remember here, it is set at standstill because we know that when the rotor will gather some speed, then the rotor reactance will change, which is the property of the induction motor, and the magnetizing reactance of the stator circuit is given as 53.5 ohms. So these circuit parameters we have to use to construct the equivalent circuit, and then we have to calculate what is the mechanical power output of this machine. Now the slip is given 0.05, so it means some speed is also given for this motor. Let us begin with the equivalent circuit and then we will solve the problem. So the equivalent circuit of the single phase induction motor, which is shown here, if we see here, R1 and X1 represent the stator parameters of resistance and the reactance. So you have a supply voltage V, which is single phase AC voltage, which is drawing a current I1. As we know that single phase induction motor, we have discussed the concept of double field revolving theory, where you have the forward field and the backward field. So it will have different impedances offered given by ZF and ZB. So here the rotor circuit is divided into two parts, one for the forward field and another for the backward field. Each is having its own resistance and the reactance, which is half of the given value. The value of the magnetizing reactance Xm is also given for the circuit. Now it should be remembered, 1 is for stator and 2 for the rotor. Again, if we see, the stator parameters are given in capital letters R1 and X1, whereas the rotor parameters are given in small caps, which means that the resistance R2, which is in small cap, will be equal to the resistance R2 divided by 2. So it is half of the given parameters that we have for the resistance and the reactance as well as the magnetizing reactance Xm. So all small caps letter is nothing but the half of the given value. If we neglect the core losses or include the core losses, the circuit will be different. So you can have one resistance RC, which is included in the circuit if we need to have the core loss into consideration. If there is no core loss, you can remove the RC from the circuit. So the impedances that we have is for the stator, which is Z1, and the impedance that we have for the rotor is Z2. Again, the Z2 is divided into the forward field, which is given by ZF, and the backward field given by ZB. If you see here, we have given some nomenclature or the node number. This node number is given for the easy way of calculating the parameters. So whatever the current is coming from the supply, it can go towards the different parts of the circuit, and we can have easy way of calculating the parameters if we give proper node number. So we will use the node numbers to differentiate the different parts of the circuit. So from the given parameters, we have to first obtain the half value of the magnetizing reactance, the rotor resistance and the rotor reactance, which is half of the given value. And these parameters are 26.7 ohms, 1.78 and 1.28. So we have got the value of R2, X2 and Xn. So these values we have got it from the circuit parameters. Now the forward field react impedance ZF we can calculate from the series parallel concept, where we have the parallel network consisting of the magnetizing reactance, the rotor resistance and the rotor reactance. So we can calculate the total impedance ZF, which is due to the forward field, using this formula, and do some manipulations and calculations to make the calculation easier. So the final answer that we get is 21.15 with angle 54.2 degree for the forward impedance ZF. Now same thing we can do for the backward impedance, which is having the combination of the rotor parameters, having reactance, resistance and the magnetizing reactance. Here the slip will be 2 minus s times. So we do the calculation and find out what is the value of the backward field impedance, which is 1.51 angle 56.3. The total stator impedance Z1 is the summation of R1 plus J times X1. J is nothing but iota term, which is imaginary, under root of -1. So electrical engineering, we don't take I, but we take J to make the calculation easier. And we take I value for the current. So to differentiate I and J here denotes the iota value. So the impedance Z1 is nothing but 3.16 angle 54 degree. This is the stator impedance involving the resistance and the reactance. Now we are in a position to find the total circuit impedance, which is Z01. We take it. It is the summation of Z1, that is the stator impedance, and the rotor impedance is a summation of the forward field and the backward field. We have calculated all these parameters, so we can substitute it in this equation to find what is the value of Z01, which gives to 25.85 angle 54.3. So this is the total circuit impedance of the single phase induction motor. Now having known the total impedance, magnitude and the phase, we can obtain what is the current. So current is nothing but voltage divided by the impedance. So it is Z01. We get 4.27 ampere as the magnitude of the current. Similarly, we can obtain what is the voltage of the forward field. So it is I1 multiplied with the forward impedance magnitude, which is gives to be 90.4 volt. The same calculation we can do for the backward field, which is the product of I1 into ZB, the backward impedance. So that is 6.44 volt. Now the impedance which we have in the path, which is denoted by 3. So that is under root of R2 by slip square plus X2 square. This is the magnitude of Z3. So that is equal to 35.7 ohms. And the path denoted by the fifth node, you have the total impedance as 1.57 ohms. So the current which is flowing in the path 3 is given by Vf by Z3, whereas the current which is flowing in path 5 is Vv by Z5. So these are the values that we get it for the current flowing in path number 3 and the path number 5. Now the torque in the forward field we can obtain from the current I3, which is I3 square R2 by S. So that is equal to 228 synchronous watts. Whereas the backward field we get it in the path number 5. So it is I5 square R2 divided by 2 minus S, and it gives to be 15.3 synchronous watt. The total torque is the difference of the forward torque minus the backward torque. So that comes to be 212.7 synchronous watts. And the output power that was asked in the problem is basically synchronous watt multiplied with 1 minus S. And this is the formula that we have already discussed in the lecture part. So that gives to be 202 watt. So this is the final answer which we need to obtain for problem number 1. Problem second, where you have 120 volt 60 hertz 4-pole single phase induction motor, and the approximate equivalent circuit is shown here. This we need to consider. And when the rotor is rotating at a speed which is given as 1764 rpm, we have to estimate the torque what it develops. We have to disregard the effect of magnetizing impedance. So we need not to take the magnetizing impedance into account. This is the approximate equivalent circuit on the single phase induction motor. And all the parameters, if we see here, it is already given. So this is the stator parameter denoted by Z1. And these are basically the parameters of the rotor under the condition of forward field and backward field. The core losses and the magnetizing impedance also is given to us. So let us see the solution. So the speed given is 1764 rpm. So we can obtain the slip value, which is nothing but the synchronous speed minus the rotor speed divided by the synchronous speed, which comes to be 0.02 per unit. So the total impedance on the circuit we can obtain by adding all the path impedances, and that gives to be 5.34 angle 13 degree. So this is the total impedance on the circuit. And then the current we can obtain as voltage divided by the impedance. Voltage is already given 120 and the angle reference is 0 degree. The impedance we have obtained 5.34 angle 13 degree. So that gives to be the current as 22.48 angle minus 30. The torque now we can calculate from the formula that we know from the double revolving field concept of the forward condition and the backward condition of the field. It gives to be Im square by omega s. Now this omega s is the synchronous speed, and we know that omega is nothing but 2 pi n by 60. So we can put it in this calculation, and the final torque that we get is 13.27 Newton meter. Problem number 3, where you have a 220 volt 6-pole 50 hertz single phase induction motor, and the circuit parameters are given of the stator and the rotor, and this is referred to the stator. So all the rotor parameters are already referred to the stator. We have to neglect the magnetizing current. So we need not to consider the magnetizing current. If the motor is running at 97% of the synchronous speed, so this is the information which is given for the slip, compute the following parameters. That is the ratio of the EMF due to forward field by backward field. What is the ratio of forward voltage by backward voltage? What is the ratio of the torque forward by backward? What is the gross total torque? The ratio of forward torque by the total torque, and the backward torque by total torque. So using the equivalent circuit, we have to obtain these parameters, basically calculating the impedances and obtaining the voltage and the torque. So let us see the solution. So from the given condition that this motor is running at 97% of the speed, so this gives the slip value is 0.03 per unit. And the equivalent circuit now we can use for single phase induction motor are the forward field and the backward field with the stator parameters and the rotor parameters. And the EMF for the forward field and the backward field, we can obtain the ratio in terms of its impedances, ZF by ZB. So the ratio of these impedances is nothing but the ratio of the impedances, and impedances we can calculate for this part separately and this part separately and put it in this equation to get the ratio of the forward impedance by backward impedance. It is already said that we have to neglect the current which is in the magnetizing. So X is infinity because the current is neglected. So we need not to take the X component in the calculation, and putting these all the data that we know from the parameters, we get the value of the ratio of the impedance is 23.38, which is again the ratio of the forward EMF by the backward EMF. Now again, we have to obtain the circuit in the in a symmetrical format to make the calculation easier, so that we divide this stator parameters in half of its value in the two part to make the circuit symmetrical, so that we can obtain the impedances and the voltage of the forward field and the backward field. So what is the impedance which is offered to the forward field and impedance offered to the backward field? We can obtain from these parameters, which is the calculation makes easier if we take the circuit in the symmetrical form. So this part of the circuit will be the forward part, and this part of the circuit will be the backward part. So you calculate the impedances which you offered for the forward and the impedance which is for the backward field, and take the ratio. You will get the voltage ratio VF by VB. In the previous part, we have calculated up to this part, which is EMF and EMB, but now we have to calculate here VF and VB, taking the stator into account. So that comes to be 6.73. So the ratio of the torque TF by TB is nothing, is basically the air gap power equation. So PGF by PGB. So we know that torque is again proportional to the power in the air gap. So this ratio formula, which is for the rotor circuit, we know we take it for the power for the forward field and the power for the backward field. These two torque equation we can use, and that gives to be the ratio 2 minus S by S, and this comes to be 65.7. So this is the ratio of the torque in the forward field condition and the backward field condition. Now to obtain the other parameters, first we have to obtain the total impedance seen from the stator terminal. So this is the total impedance of the circuit involving all the parameters of the stator and the rotor referred to the stator, so which comes to be 29.2 angle 13.9. So the current is nothing but the voltage divided by the impedance magnitude. So this gives to be 753 ampere. The speed we can obtain the synchronous speed and the speed in radian per second. So again, we know that the synchronous speed is given by 120 F by P. So frequency is 50 Hz and the number of poles is 6. So that gives 1000 RPM as the synchronous speed of the machine. So the synchronous speed in radian we can obtain as 2 pi ns by 60. So that comes to be 104.72 radian per second. So the torque calculation we can do for the forward field and the backward field, and total torque again will be the difference of the forward field and the backward field. So the total torque of the machine we have to calculate as the difference between forward and the backward field, and all the parameters we can substitute in the main equation to get 13.31 Newton meter. Now the final part of the problem asks that we have to find the ratio of forward field by total torque and the backward field by total torque. So forward by total torque equation, we can get it in terms of the slip equation, which gives to be 1.015. Backward torque by total torque, again we can obtain from the slip ratio, so that gives to be 0.015. So we complete here the second part of the single phase induction motor, when we have discussed the equivalent circuit and calculated the torque, power and its corresponding impedances. The final part we will discuss in the coming tutorial, where we will see the testing, that is the no load and the block rotor test of the single phase induction motor. So stay tuned. Thank you for now.